Okay, now we're going to deal with the second part of rotational dynamics, which is torque, moment of inertia, and angular momentum. Okay, we'll get started with the torque here. So if I apply a force to a door, we're looking at the door from top view, okay, and I provide that at an angle, theta, and we'll write that right here. It is the perpendicular part of that force that causes rotation to happen. So I'm going to draw that in here. Here's our vector. Okay, there is another force that's parallel to the door, which of course does not cause rotation to happen. So our angle theta is also here. So if I want the perpendicular part of this, if this is my force here, the perpendicular part then would be governed by the sine of the angle theta. And we have a distance d all the way to the point of rotation. I'll label that d. So therefore torque is force times the distance to the point of rotation multiplied by the sine of the angle theta. Now what are some applications of that? Well, if I have some books here and I want to find out how much force needs to be applied, okay, and this is a class A lever arm, I've got a distance, okay, from that force to the point of rotation, and I have another situation here where I've got gravity pushing downwards. Now remember that all the gravity of these books looks like it'll come from one central point from inside, and that has a different distance to the point of rotation. Rotation is our fulcrum here. Okay, so then the torque going in this direction here, which is clockwise, we make negative, and the torque going in this direction is positive. So the books will cause positive rotation, and that force will cause negative rotation. So we then say the sum of all torques equals 0. And let's just call this force gravity here. Will equal force gravity. And let's call this distance x and this distance here y. So force gravity x. Okay, and I'm not going to include the sine of theta this time because we are at 90 degrees. And then we'll say minus that force multiplied by the distance y. So if we know our distances, we can easily figure out our force required to hold those books up. What about another application? A simple bridge. So we can think of a simple bridge as two rotation points. And if we're trying to figure out what force normal is in both of these beams, we'll draw the first one in here, second one there. So let's call this one force normal 1, and this one here would be force normal 2. Okay. We will then have a force gravity straight downwards from somewhere in the center of mass of the car, probably closer to the engine, but we won't worry about that detail. And then we'll have a center of mass of our beam coming from the exact center. Okay, from all the mass of that beam looks like it's coming from its center. Okay, so then we will have a distance d. Okay, and then we'll just use x and y's again for that. So we will have a distance to the point of rotation. Okay, if I choose this point as my beginning rotation, and then we'll have another point of rotation here like that. Let's call this one x, and we'll call this one y. Now, since this is our point of rotation here, we can say the sum of all torques is equal to 0. Let's call this force gravity 1, and this one will be force gravity 2. Okay, these two cause clockwise torques to happen, so therefore negative, and force normal 2 will then cause positive torque to happen. So we're then going to say force gravity 1 multiplied by x, and we'll make that negative. And again, we're perpendicular, so I won't put any signs there. And that would be minus force gravity 2 times y plus force normal 2 multiplied by the whole entire distance, okay, to the point of rotation. And then we'll just call that distance d. Okay. And again, that's the distance from this point all the way to that point of rotation. Since all that would equal 0, we can figure out force normal 2, because we'll know our distance x and our gravity, our distance y we'll know, and our distance from here all the way to there we'll know. We can just find force normal 2. Now to find force normal 1, we can do the second condition, okay, of equilibrium. The sum of all forces equals 0. So this would be the first condition of equilibrium. The sum of all torques equals 0. The second condition would be the sum of all forces equals 0. So sum of all forces in the y direction equals 0 equals force normal 1, that'll be a positive pointed upwards, plus force normal 2, that's a positive one pointing upwards, minus force gravity 1, minus force gravity 2. Since all that will equal 0, we will know force normal 2, we'll know force gravity 1 and 2, we just figure out force normal 1. So instead of going back and using torque, again, I like to use the second condition of equilibrium there. Okay, scaffold will run just like a simple bridge, except we have force tensions instead. So we'll call this force tension 1, and this one will be force tension 2. And of course, we'll have a gravity going straight down, okay, from the center of this beam. And then we'll have the gravity of this duct straight down there. And if we give a point of rotation right here, again, we'll just do the sum of all torques again. The sum of all torques would equal 0. We need to identify our distances. So we'll have a distance from here to there from the center of our plank. Another distance from here to there from where the duct is located. Okay, so let's call this distance here x, and this distance y. And of course, we'll have a total distance there. So that's going to equal then, and we'll just call this one force gravity 1, and this one's force gravity 2. So it'll be a minus force gravity 1 multiplied by x minus force gravity 2 multiplied by y, and then plus a force tension 2 multiplied by d. So you see a very similar equation. Then we can use sum of forces in the y direction to get our force tension 1. But one final mention here. Let's look at our y value here and our x value here. Okay, so x is actually going to equal d divided by 2 in this case. It always comes from the center location, so from the center. And that would also apply to our simple bridge. We always see that all the gravity from the object looks like it comes from its actual center. And that's how we handle those conditions of torque. More to come in our next video.